deep into the heart of matter, the fundamental bits that make up protons and neutrons. But here's the kicker, the really strange part. We've never actually seen one of these building blocks just on its own. And I was talking about quarks. How can something so fundamental, the very essence of the stuff around us, stay hidden like that?
It is a pretty profound question, yeah. And the answer, well, it lies in the fascinating, sometimes weird, rules of the subatomic world. We're talking about the absolute basic ingredients, the things that combine to form larger particles we call hadrons. That includes protons and neutrons, obviously, but also a whole zoo of other more exotic particles. And yet, yeah, these quarks are never found alone, always stuck together in these composite states.
Exactly. So our mission for this deep dive is to sort of unravel this mystery. We'll look at the incredibly strong indirect evidence that has, well, really cemented the existence of these elusive quarks. Forget trying to wade through dense textbooks. We're going to piece together the story using, surprising experimental results and these powerful theoretical ideas. Think of it like, I don't know, scientific detective work. The clues are hiding in how other particles behave.
And what's really remarkable is just how many different clues there are. It's not like we're relying on just one experiment or, one single theory. Instead, we've got multiple independent lines of evidence, and they all point towards the exact same conclusion. It's quite a testament to the ingenuity, the persistence of physicists over decades.
All right, so where does our quark detective story kick off? It sounds like the late 60s, early 70s were pretty crucial. Something big happened at SLAC.
That's right, SLAC, the Stanford Linear Accelerator Center. The Deep Inelastic Scattering experiments, or DIS, they were absolutely pivotal. Basically, imagine firing incredibly high-speed probes, in this case, electrons at protons and neutrons, trying to see what's inside, essentially.
Okay, so if protons and neutrons were just solid little balls, fundamental, indivisible, what would you expect to see? The electrons just kind of glance off?
Pretty much, yeah. If they were solid, fundamental things, the electrons should have mostly just, bounced off with a small change in direction, maybe lost a tiny bit of energy, like hitting one billiard ball with another. But what they saw was dramatically different. A lot of electrons scattered at really large angles, and they lost a lot of energy. This hard scattering, as it was called, was a huge surprise. It was the first big clue that something wasn't quite right with the idea of protons and neutrons being elementary.
Oh, hot scattering.
Right.
That sounds key. Why was that so important, so unexpected?
Well, because it immediately brought to mind Rutherford's famous gold foil experiment, right? Firing alpha particles at gold foil. Most went straight through, but the odd one bouncing back at a large angle. That revealed the atomic nucleus, this tiny, dense core. The hard scattering at SLAC suggested something similar inside protons and neutrons. They weren't fundamental. They contained smaller, hard, almost point-like things. So the big aha moment here was realizing protons weren't these smooth, indivisible marbles people thought. This hard scattering. That was the clue. Something smaller, harder inside.
And these internal somethings, Bjorken called them partons. And his idea of scaling was important for making sense of it all. Okay, what was this scaling idea? What did he predict?
Exactly, James Bjorken, yeah. He predicted that if protons had these point-like, almost free particles inside the partons, then the way the electrons scattered wouldn't depend separately on the electron's energy and how much momentum it transferred. Instead, it would depend on a particular combination of those two things. That's Bjorken scaling. It's like the internal structure, these little bits, responds to the probe in a way that depends on overall oomph of the collision, not just its specific energy or momentum transfer individually.
And the SLAC experiments, they actually saw this scaling. It worked.
They did, yeah. The data matched Bjorken's scaling prediction remarkably well. This was really powerful evidence that protons and neutrons weren't uniform blobs. They had internal point-like constituents. So yeah, the bottom line from SLAC was a shocker. Protons have stuff inside, behaving like tiny points.
Wow. And then by looking closely at how these electrons scattered the angles, the energy they lost, physicists could figure out the electric charges of these partons. And they turned out to be fractions, like plus 23 and negative 13, the charge of an electron. That matched the quark model predictions. That's wild.
Precisely. The detailed analysis showed these partons had these weird fractional charges, plus 23e and negative 13. This was just a stunning confirmation of the quark model that Gell-Mann and Zweig had proposed a few years earlier, kind of on theoretical grounds. At that point, identifying these partons as quarks became, well, almost inescapable. So the key insight wasn't just that protons had structure, but the absolutely bizarre nature of the charges inside.
Okay, so SLAC wasn't working in a complete vacuum. You mentioned Gell-Mann and Zweig. Even before this DIS evidence, there was already this theoretical idea, the quark model, right?
Yeah.
And it was doing a pretty good job organizing the particle zoo of hadrons discovered back then.
Absolutely. Yeah, back in the mid-20th century, particle discoveries were just exploding. It was chaotic. Then 1964, the quark model comes along. It offered this surprisingly simple, elegant way to make sense of it all. It basically said all these different hadrons could be built from just a few fundamental blocks, quarks. So even before SLAC saw them, the model was already providing this powerful, unifying explanation for tons of known particles.
And the model gave specific recipes for different hadron types, baryons and mesons. What were the combinations?
Yeah, it laid it out. Baryons, like protons and neutrons, were 3 quarks stuck together, QQ. Mesons, like pions, were a quark and an antiquark, Q-bar. So for instance, a proton is 2 up quarks and 1 down quark, and a neutron is 1 up and 2 downs. It provided this underlying structure, a way to classify this huge number of particles.
And it wasn't just counting quarks. The model used quantum numbers for different quark flavors, initially up, down, and strange to explain hadron properties like spin and other things.
Exactly. Spin, isospin, strangeness. These are like intrinsic properties, labels the quarks carry, kind of like electric charge. And these properties dictate how quarks combine and how the resulting hadrons behave. The model brought amazing order to the chaos, but, even more impressively, it made predictions. The most famous one has to be the omega minus baryon.
Oh, yeah, the Gary, that was predicted before it was found, based on the quark model pattern, right? And its properties were spot on. That's huge.
A massive triumph, yeah. The omega minus is 3 strange quarks. The model didn't just say it should exist, it predicted its mass, charge, spin, even how it should decay. When it was actually discovered in '64 at Brookhaven and everything matched up almost perfectly, well, that was incredibly strong support for quarks being real. Predicting not just the particle, but getting its properties nearly exact. That's like, yeah, a detective predicting a suspect's height, weight, and coffee order before meeting them. A huge win.
Okay, but wait. Quarks are fermions, right? They have spin 12. So having 3 identical quarks, like 3 up quarks in the O particle or 3 strange quarks in that A, doesn't that violate the Pauli exclusion principle? You can't have identical fermions in the same quantum state. How did they fix that?
That's a really sharp point. And yes, it was a major puzzle for the early model,
really?
head scratcher. The solution was brilliant, actually. They proposed another fundamental property, color charge. Each quark comes in one of 3 colors. Let's call them red, green, and blue. Antiquarks carry anticolors entire anti-green, anti-blue. Now, super important, this has absolutely nothing to do with visual color. It's just a label for this new type of charge, this quantum number.
Color charge? Okay, not visual color, just another kind of charge quarks have. Got it.
Yeah, exactly. And the crucial rule, the postulate, is that all observable particles, all the hadrons we actually see, must be colorless or color neutral. Their net color charge has to be 0. For baryons, the 3 quark particles, you get color neutrality if you have 1 red, 1 green, and 1 blue quark, like mixing light colors to get white. For mesons, the quark-antiquark pairs, you need a color and its matching anticolor, like red and antired. They cancel out. This requirement that only color-neutral combinations can exist freely is basically the reason for confinement. An isolated quark would have a net color, which is forbidden by the strong force rules.
So introducing color meant you could have 3 up quarks in the delta plus plus, as long as one is red, 1 green, 1 blue. They aren't identical in all quantum states anymore. Problem solved. And this color neutrality thing, only seeing colorless combinations. That's the heart of confinement.
Precisely. That's the link. The strong force, which acts between these colored things, quarks, and also the force carriers, gluons, it behaves really strangely compared to, say, electromagnetism. The electromagnetic force gets weaker with distance. The strong force, it gets stronger as you pull quarks apart. It's often compared to a rubber band or a spring connecting them. The more you stretch it, the harder it pulls back. If you try to pull 2 quarks apart with enough energy, the energy stored in that spring gets so huge that it's actually easier to just pop a new quark-antiquark pair out of the vacuum energy. These new quarks instantly pair up with the ones you were trying to separate, forming new color-neutral hadrons. You never, ever end up with a single colored quark by itself.
Okay, that makes sense now. You can't just knock one out because the energy you put in just makes more quarks and keeps everything colorless. But what about those electron-positron annihilation experiments you mentioned? How do they give us another angle, another way to seize quarks?
Right. These EU experiments offer a different, very compelling kind of evidence, almost like seeing quark footprints. When you collide a high-energy electron and its antimatter twin, a positron, they annihilate. Poof. all their mass turns into pure energy. This energy often takes the form of a virtual particle, like a temporary burst, which can then instantly rematerialize into other particles. Very often it turns into a quark and its corresponding antiquark, flying off in opposite directions.
And that new quark-antiquark pair,
Hmm.
they can't just fly off freely because of confinement, right? Based on what we just said.
Exactly. Confinement kicks in immediately. As that quark and antiquark start moving apart, the strong force between them ramps up intensely. Just like we discussed, this rapidly increasing energy leads to more quark-antiquark pairs popping out of the vacuum along the line between them. These newly formed particles quickly combine with the original pair and with each other, forming two sprays or jets of color-neutral hadrons. And crucially, these jets tend to fly out back-to-back, roughly in the same directions the original quark and antiquark were heading.
So when the detectors see these two distinct narrow cones, these back-to-back jets of particles spraying out from the collision point, that's basically the visible aftermath of that initial unseen quark-antiquark pair.
That's a really good way to put it, yeah. The jets are the directly observable consequence. The fact that we consistently see these two collimated streams and that analyzing the particles within the jets tells us they likely originated from spin 12 particles, like quarks should be, that's very strong evidence for the whole picture.
And you also mentioned seeing three-jet events sometimes. What's going on there? What does that tell us?
Good question. Occasionally, before the initial quark or antiquark turns into a jet of hadrons, that process is called hadronization, by the way, it can radiate off a high-energy gluon. Now, the gluon itself carries color charge, so it can't exist alone either. It also undergoes hadronization, creating its own jet of particles. So when we see three distinct jets coming from the collision, well, that's interpreted as the original quark, the original antiquark, and a gluon all turning into jets. It's not just more evidence for quarks, it's really direct evidence for the existence of gluons, the strong force carriers, behaving as spin-1 particles, just like the theory predicts.
It's like we're seeing the whole chain reaction. Quark, antiquark created, maybe a gluon gets radiated, then boom, they all blossom into these detectable jets.
Yeah.
Now, what about heavy quarkonium spectroscopy? That sounds pretty technical. What's the basic idea, and how does it fit into the quark puzzle?
Think of it like studying the atoms of the strong force. It's a really neat analogy. You know how a hydrogen atom is an electron bound to a proton by the electromagnetic force? Well, quarkonium is a bound state of a heavy quark, like a charm quark or a bottom quark and its own antiquark. They're bound together by the strong force. And because these charm and bottom quarks are much heavier than the up and down quarks, they tend to move around relatively slowly inside this quarkonium atom. They're sort of non-relativistic. This slowness makes things a bit simpler mathematically. It allows us to use potential models, kind of like we do for atoms, to predict their behavior, especially the energy levels they can occupy.
Okay, so systems like charmonium, charm plus anti-charm, and bottomonium, bottom plus antibottom, are like these mini quark-antiquark systems governed by the strong force.
That's a great way to think about it. And these potential models predict a whole spectrum of distinct energy levels, or masses, for these bound states. Each level corresponds to a specific configuration with particular properties, spin, parity, things like that. The really amazing thing is when experimentalists actually create and measure these charmonium and bottomonium states, their measured masses and other properties match the theoretical predictions from these models with just astonishing accuracy.
And this incredibly precise match between the predicted energy levels and the experimentally observed particles, that's more strong evidence for these heavy quarks existing. And it tells us about the strong force, too.
Exactly. The precision is key. It confirms not only that heavy quarks like charm and bottom are real, but it also gives us incredibly valuable information about the shape of the strong force potential, how the force behaves between quarks at different distances. We learn it's sort of Coulomb-like, similar to electromagnetism, at very short distances, but then it starts rising, becoming stronger linearly at larger distances, which is related to confinement. It's like testing the blueprints of the strong force itself.
So all this experimental evidence, the scattering, the particle zoo patterns, the jets, the heavy quarks, it all seems to point in the same direction. But you also mentioned the big theory that holds it all together. Quantum chromodynamics, QCD. How does QCD unify all this?
Right. QCD is the fundamental theory of the strong interaction. It's the mathematical framework describing how quarks and gluons interact, using color charge as the key ingredient. And maybe its most crucial and initially surprising feature is something called asymptotic freedom.
Asymptotic freedom. Sounds almost like a contradiction. Freedom when things get closer or higher energy. How does that work?
It does seem counterintuitive, doesn't it? Asymptotic freedom means that the strong force coupling, its effective strength, actually gets weaker as the energy of the interaction goes up, or equivalently, as the distance between the quarks gets smaller. This is precisely why, in those high-energy, deep inelastic scattering experiments we started with, the partons, the quarks inside the proton, looked almost free when the high-energy electron probe hit them. At those tiny distances, the strong force is relatively weak.
Ah, okay. So very high energy, very short distance. Quarks act almost free.
Hmm,
But at lower energies, larger distances, like the size of a proton, the force becomes incredibly strong, leading to confinement. It's the opposite of electromagnetism or gravity.
precisely. At everyday energy scales, or distances comparable to the size of a hadron, the strong force coupling is huge. It's practically impossible to pull quarks apart. The energy needed just keeps growing until it's easier to create new pairs. So asymptotic freedom at short distances and the strong coupling leading to confinement at larger distances are really two sides of the same QCD coin. Both are fundamental.
And QCD, as this complete theory, has been massively successful, right? Explaining everything from hadron masses to jet patterns, even stuff happening inside neutron stars.
Absolutely. Its internal consistency, its predictive power across just a vast range of phenomena and energy scales, it's truly remarkable. QCD is a cornerstone of the standard model of particle physics. It provides the robust theoretical framework that elegantly explains all these different pieces of indirect evidence for quarks that we've been talking about.
So we've kind of come full circle, haven't we? Back to that initial paradox. These fundamental particles making up so much of the visible universe, yet they're perpetually locked away inside other particles. But through these incredibly clever experiments, smashing things together, analyzing the debris meticulously, and combining that with the deep insights of QCD, we've built this, well, overwhelming case for their existence. We've essentially managed to see the unseeable by figuring out the consequences of their actions.
Exactly. The evidence is multifaceted. It's robust, coming from so many different angles. Disks, hadron patterns, jets, quarkonium, all underpinned by QCD. It all converges. Quarks are real. They have the properties theory predicts. And they are the fundamental constituents of hadrons, even if the bizarre nature of the strong force means we can never catch one all by itself.
It really makes you think, doesn't it?
Uh-huh.
About how we understand the universe.
Yeah.
Our grasp of reality at its most basic level relies on being able to infer, to indirectly see things that seem impossible to observe directly. Makes you wonder, what other hidden aspects of the universe, things that seem unseeable now, might we eventually figure out through, even more ingenious experiments and maybe even newer theories down the line, something to chew on?